So these are the instructions. How do you do this? First, draw the Lewis structure. 2, find the number of electron groups on the central atom. Figure out how many are bonding and how many are lone pairs. And then I think this is so silly of your book. Their instruction is refer to table 10.1. Well, that works great for homework. Doesn't work on an exam, right? So don't do that. Do it if you have to. And cross that off. Think about how balloons would arrange themselves, and imagine that the lone pairs are invisible balloons. And if you practice that a little bit, you'll be able to do all the geometries without much trouble. How do we draw these things on paper or on a two-dimensional screen? Well, we use wedges. There's hatched wedges, which go behind the paper, and there are solid wedges which stick out of the paper. And if we just draw a straight line, that's in the plane of a paper. Now, linear is easy to draw. Trigonal planar, easy to draw. Bent is fine. Well, they don't have T-shaped in here. That one's easy. Square planar is fine. The rest of them are not flat, and so they're tricky. So let's look at the tetrahedral. We usually draw these with 2 of the groups in the plane of the paper. So there's the X, A, X. That's flat in the paper. This X is sticking out at you, and this one's behind. And that's how we represent three-dimensional things in a two-dimensional space. For this trigonal bipyramid here, we have the axial X's up and down. This one's sticking off to the side in the plane of the paper. This X is sticking out at you with the solid wedge, and the hatched wedge is behind the paper. It's like a dashed line. You can't see it. It's behind the paper. Any questions? You could just draw the double bond. You would want to try to put that in the plane of the paper. Usually when we're drawing things with wedges and stuff, we're not so concerned about the double and triple bonds. But yeah, you can't really do a double wedge. It doesn't work so good. What about larger molecules? Because there are a lot of molecules that have more than one central atom, right? When that happens, what we do is we look at each of the interior atoms. So here's this fine molecule. And we've got nitrogen, carbon, carbon, and oxygen. We have 4 interior atoms. So we're going to look at the Lewis structure for this. This is glycine, which is an amino acid. And we're going to look at this nitrogen, and we're going to count the electron groups. 1, 2, 3, 4. 4 groups, tetrahedral. But one of those is invisible. So that is a trigonal pyramid. So the nitrogen has a trigonal pyramid shape. This carbon has 4 groups, no lone pairs. That one's tetrahedral. This one has 3 groups. One of them is a double bond. 3 groups is trigonal planar. So this one forms a triangle. And then we've got the oxygen over here with 2 lone pairs and 2 bonds. And that gives a bent structure. And so that's drawn as bent. And these get pretty tricky if you try to draw them in 3-dimensional space on a 2-dimensional piece of paper. That's where computers come in really handy. But this sort of a skill is very important if you're going to go on and take organic chemistry, is to be able to look at these different atoms and identify what their geometry is, because that really helps predicting the shape of the molecule. Let's predict the geometry around each interior atom in acetic acid and make a sketch of the molecule. Fun. Well, we need to know about any lone pairs. In fact, that's all very nice and everything, but it's not really drawn out enough. So we've got 3 hydrogens on this carbon. Let's draw them out so we can see them. There's a carbon and a double bond and an oxygen and a bond to hydrogen. Is this carbon okay? octet rule-wise? And this one? Yeah. How about this oxygen? He's not so happy. He probably is going to have 2 lone pairs. How about the other oxygen? He's going to have 2 lone pairs too. And if you don't believe me, you can go through there and figure that out for yourself. So if we look at this carbon, how many electron groups? 4. The electron geometry is what? Tetrahedral. Are there any lone pairs? No. So the electron geometry and the molecular geometry are the same. This one's tetrahedral. What about this carbon? What's the geometry around that? There's 3, and there's no lone pairs, so that's trigonal planar. And what about this oxygen? Bent. 4 groups is tetrahedral. 4 groups tetrahedral, 2 lone pairs. So you envision the tetrahedron, and then 2 of those balloons are invisible. What's left? You just have 3 atoms left, and it's bent. So now we're going to try to draw this. Well, I'm going to start with the tetrahedral one because that's the hardest. So I'm going to make this carbon in the plane and that hydrogen in the plane. I'm going to stick this one out and this one behind. So that's the tetrahedral carbon. This carbon is trigonal planar. And so we have the oxygen and the other oxygen over here. These are going to be 120-degree angles all around. That one's flat. It's all in the plane of the paper. And then this oxygen is bent. And so that's going to be off like this to the hydrogen. So carbon, carbon, oxygen, oxygen, hydrogen, those can all be flat in the plane of the paper, and this hydrogen too. But this hydrogen is going to be behind, and this one's going to be in front. Any questions?